morning everyone. Myself Dr. Deepak Yadav, and today we will discuss the topic, some complex topic of antenna and wave propagation subject, that is one of the mandatory subject of third year, in which we go for the topic that is wave propagation. So in this wave propagation topic, we will discuss about different wave mechanism like ground wave propagation, sky wave propagation, and tropospheric wave propagation. So one by one we will deal with these topics. In the initial stage, we will go for the brief introduction of all these kinds of wave that is propagating in the medium. Like we have a three kind of wave that is propagating in the free space, that is ground wave, sky wave, and space wave propagation. So in ground wave propagation, the wave generally that is travel along the surface of the wave, along the surface of the ground, like multiple bump it can create, and the ground and the tropospheric outer layer is behave as a guided medium for the ground wave propagation. In sky wave propagation, the wave is go into the into the sky, which is very deep in the ionosphere, and due to the change in the electron density of the ionosphere, there is some mechanism take place which reflect the wave back to the earth. So with the help of this sky wave propagation, we can use ionosphere to transmit the wave for the long distance. So generally the distance for the ground wave is short, but the sky wave is very large. Or in case of space wave propagation, the wave travel from transmitter to the receiver directly. Either it follow the direct path or by a single bump from the surface of the earth. So these three mechanism are we are going to discuss today. So these three mechanism is like this. It is known as, first one is known as ground wave propagation, another is known as space wave propagation, and third one is known as sky wave propagation. The range of the ground wave propagation is very short, while the range of the space wave propagation is medium, up to for 50 kilometer, 60 kilometer, and for the sky wave propagation it is thousands of kilometer, because the wave is reflected from the very upper layer of the atmosphere, that is ionosphere. So these are the some frequency range over which these wave propagation take place. Like first one is the ground wave propagation. So for the ground wave propagation, the frequency use up to 2 megahertz. After this, higher frequency get absorbed very much by the atmospheric absorptions and by the multiple bumps. So the next is space wave propagation. In case of space wave propagation, ultra high frequency wave range is used. Over 300 megahertz is used. In this communication, the wave is directly travel from transmitting antenna to the receiving antenna. So there is no absorption take place, or it is a very high frequency. So the distance again is very short, only up to the horizon of the earth. And these wave are used for ultra high frequency range are used for space wave propagation. While in sky wave propagation, this band is very much fixed from 2 megahertz to 30 megahertz only, because the phenomena, that is total internal reflection, is used by the ionosphere to reflect these waves back to the earth. So this phenomena happen only within the range of 2 to 30 megahertz. Next is space wave or tropospheric wave propagation. So the second one, that is tropospheric wave propagation, is used troposphere of the Earth atmosphere as a medium. So troposphere is exists from the Earth surface. This is the Earth, and it is exists from the Earth surface to the 15 kilometer height from the Earth surface, and that is known as troposphere. So the wave is traveling either from the transmitting antenna to the receiving antenna, either direct or by a single bump from the Earth surface. So if these two waves are involved in the communication, this kind of propagation is known as space wave propagation, and it is carried out over a frequency range of 300 megahertz. So this is one of the classification of space wave propagation. So you can see in this picture, this is the diagram of the Earth and its atmosphere. This is troposphere, this is the stratosphere. this is exists, this troposphere is exists from 0 to 15 kilometer, and the transmitter and receiver is exist within this range, like the transmitting antenna or the receiving antenna height is over the range of 50 meter to 100 meter. So the signal is goes direct from transmitter to receiver or by a bump from the earth surface. There is one thing, that is line of sight. So the line of sight is nothing but if a transmitting antenna is in the visible range, is in the visible range of the receiving antenna, then this range is known as line of sight range. Due to the curvature of the earth, if the antenna of transmitting and receiving antenna are going further far, then the direct contact, the direct line of sight is changed and it is obstructed by the curve of the earth. So the direct wave is not reaches from the transmitting to the receiving antenna. So in this case, direct propagation is not possible. The application of these tropospheric wave are we use in TV, radio, radar and FM radio transmission. So this is the multipath that is used, multipath space wave that is used from transmitting antenna to receiving antenna. The wave is goes from transmitting antenna to the receiving antenna direct or by a reflection from the earth surface. So there is two paths, direct path or reflected path. There is two type of horizon also over here, optical horizon and radio horizon. Optical horizon is that horizon over which we can directly see the see from the top of the transmitting antenna to the receiving antenna. Like if we consider again the curvature of the earth, and if your transmitting antenna is over here and your receiver antenna is over here, transmitter and the receiver. So if we can see the transmitting antenna, receiving antenna from the transmitting antenna directly, then this is known as the optical horizon. This is known as the optical horizon. While if we use the radio horizon, due to the curved earth surface and due to the ground wave or some reflection, these waves can go up to far from the optical horizon, and we can shift the transmitting and receiving antenna further and increase the range. So this horizon over which the optically it is not in the sight, but due to the radio wave reflection, it is in the sight from the transmitting to the receiving antenna, and this horizon is known as radio horizon. So range of the radio horizon is little larger in compared to the optical horizon of the space wave. So you can see this is the optical horizon. Transmitting antenna is directly in the range of receiving antenna, while in case of radio horizon, we can shift the transmitting receiving antenna further, so that we can increase the range of the transmission. So this is the radius of the earth, this is the height of the transmitting and receiving antenna. The maximum radio range of the optical range or line of sight. So this is the line of sight, optical range. And we have one derivation how we can what is the height of the transmitting and the receiving antenna, so that we can transmit the wave up to the d distance from the transmitter to the receiver. So for that we can go for the reference of this figure. This is the center of the earth O. These are the three radius of the earth. This is d1 distance in the curved shape, and this is d2 distance. This is the actual distance, that is d. This is the height of the transmitting antenna. This is the height of the receiving antenna. Now the total distance d is equal to the sum of d1 and d2. So the total distance d is equal to d1 plus d2. Small r is the radius of the earth, and it is fixed as a constant. It is 6,370 kilometer only. And these are the height of the transmitting and receiving antenna. This is in meter over here. So if we calculate d1, so what is the value of d1? So if we consider this triangle, then this is r plus t, and this is d1. So with the help of trigonometry, Pythagoras theorem, d1 is equal to under root of ht plus hr whole square. This ht plus hr whole square minus r square. This is r square. So this d1 is equal to this square minus this square under root. So you can see over here, this is d1, and if we open this square, then we have ht square plus hr plus r square plus 2 ht into r minus r square. This r square is cancelled and d1 is equal to under root of 2 ht into r. Now, if we see if this where is this ht square goes, as you can see, this is the radius of the earth, which is very large compared to the height of the antenna, which is few meter, like 50 meter or 70 meter, while the radius of the earth is 6,370 kilometer. So this ht square is very small compared to twice of ht into r. Due to this r, this factor is very small and we can neglect this factor. R square is cancelled, so the d1 is under root of 2 times of ht plus r. Similarly, for the d2, we can calculate for the d2 this square, that is ht plus hr whole square minus r square is equal to d2 square. So again, in the same way, we can open this this whole square and neglect this hr term, because again hr is very small compared to the radius of the earth. So we have under root of 2 hr into r. So the total distance d is equal to d1 plus d2. So it is written as d maximum distance is equal to under root of twice of ht plus r, ht into r plus under root of twice of hr into r. So if we take the common, that is 2r, and put it over here, then d maximum is equal to under root of 2r under root of ht plus under root of hr in meter. If we write the value of Earth's radius 6,370 and solve and take the under root, we get a value 3.57. Again we convert it into the meter. So this is converted into the kilometer. So d max is equal to under root of ht plus under root of hr. And if we approximate this value, this is approximately equal to 4. Then d max is equal to 4 times of under root of ht plus under root of hr, where ht is the receiving and transmitting antenna height and hr is the receiving antenna height. So we can see that the distance of communication between the transmitting and the receiving antenna is directly proportional to the height of the transmitting and the receiving antenna. So if we make the tower as long as large as long as possible, we can increase the range of this transmission from the transmitting to the receiving antenna. Now these are the some calculation or some examples of the transmitting or the receiving antenna height, and calculate the distance between the transmitting and receiving antenna. D max is equal to 4 if the transmitting antenna height is 225 meter over here and the receiving antenna height is 1 meter. So we can put these values. This is the square of 15, that is equal to 15, that is equal to 1, 16 into 4, that is 64 kilometer. So if your transmitting antenna height is 225 meter and the receiving antenna is only 1 meter, that is the case of the radio transmission. So you can see up to 64 kilometer we can easily travel the transmit the signal with the help of space wave propagation. Again, if we increase the height of the receiving antenna, you can see over here the range is increased by a factor of 10 or 12 kilometer over here, just by increasing the height of the receiving antenna from 1 to 16 meter. This is the another example. If the height of the transmitting and receiving antenna are given in the feet, then you can write these values in the feet over here. Then the distance is calculated in the miles over here. So like you can see over here, for 100 meter and 50 meter heights antenna, we have the maximum distance of 24.142 for the communication. If the height is very large and the receiving antenna height is almost very small, then you can take this formula as well for calculating the distance. Again, this is one of the example of transmitting and receiving antenna heights. Now the field strength relation of the sky wave. So what happened if we transmit a wave from the transmitting antenna and it travels into the space and reaches to the receiving antenna, some of the field strength got absorbed by the atmosphere or by the channel, or due to the reflection of these waves, some of the waves are penetrated into the earth and lose their energy, and also phase shift is also exist when the wave is reflecting from the earth's surface. So we can here we can calculate what is the amount of the field, electric field, that is radiated from here reach at this Rx point. So for this calculation, we use this diagram. Here, this is the Earth's surface. This is the height of the transmitting antenna HT, height of the receiving antenna. This is the path of the direct wave. It is given by R1, and this is the path of the reflected wave given by R2. If we project this R2 back to the inside the Earth's surface, it goes up to over here, and this distance, this reflection distance, is same as this is the distance, that is HR. So at the total distance, that is it is travel, is D. Then we have this larger triangle over here for the reflected wave. So now again we can consider this larger triangle, that is R1 square. We are going to consider this triangle. This R1 square is nothing but this is HT minus HR. This is HT minus HR, and this is D1. Then R1 square is equal to D1 is D square, this D square into HT minus HR whole square. HT minus HR whole square plus D square. Then we take the under root. R1 is equal to D times of this value. Now, what is happened over here, where this under root goes, this HT minus HR, this value is in meter. Like if the transmitting antenna is of 100 meter, of 100 meter, and the receiving antenna of 80 meter, then the subtraction is only 20 meter. So this HT minus HR is only 20 meter, while this D is in up to 50 kilometer in range. So this again D is very large, its square is again very large, and this is a very small value, so its square is again very small. So this factor is very small, and then we know a binomial theorem, that is 1 plus x to the power n. So if we see over here, this is possible only when x is very small compared to 1. So over here, this one is over here, and this factor is very small in compared to your value of 1. So this is very small. So in this case, we can apply the binomial theorem up to this point, 1 plus nx. This n is nothing but 1 by 2 over here. This 1 by 2 is coming in the multiplication of this factor. Then we have the R1 is equal to D 1 plus HT minus HR by 2D square. Now we can write this R1 again over here like this, using binomials theorem. Next, if we take R2, again R2, for the R2, this is the value of R2, and this R2 square is equal to D square plus HT plus HR over whole square. So now taking this value, R square is equal to HT plus HR square plus D square. We have this, again we take the common D over here, 1 plus HT plus HR upon D square, and this HT plus HR is again, that is 100 plus 80, this is 180 meter, and this D is again, if we consider 50 kilometer, then this 180 is very less than in compared to D, which is 50 kilometers, and again this factor is very small. By using binomial theorem, again we put this 1 by 2 in the multiplication of this factor, and we have the R2 is like this. Now, if we calculate the path difference between the transmitting wave that is going direct and the wave that is reflected from the Earth's surface, then the path difference is R2 minus R1. So this path difference R2 minus R1 is nothing but, this is the R2, this is the R1. If we take these values, open the square, and we find it is equal to 2 times of HT HR by D. So if we know the path difference, we can as easily calculate the phase difference between these two waves. So the phase difference, the formula is, phase difference is equal to 2 pi by lambda into path difference, and we have the path difference of 2 HT HR by D. If we solve this value, we are having the path difference after the reflection from the Earth, 4 pi HT HR by lambda D. Again, a second path difference is introduced when a wave is reflected from the Earth's surface, its phase is changed by 180 degree due to the reflection from the Earth's surface. So the another phase difference that is equal to beta, which is represented by 180 degree, and the phase difference alpha due to the path difference is given by this factor. So the total phase difference delta is equal to alpha plus beta, then alpha plus 180 degree. Now, if we consider that some amount of power that is radiated by the ED wave that is received at the receiver, and another is reflected from the earth surface, and it is given by ER, and this wave does not suffer any phase difference, because this wave goes direct from the transmitter to the receiver without any reflection, while in this case the second wave goes from some phase change, that is e to the power j alpha plus 180 degree. Now, if we consider the total field that is received, E is equal to ES 1 plus e to the power j alpha plus 180 degree. What is this ES? This ES is nothing but the magnitude of this and this, because both the wave are generated from the same transmitter, so the amplitude of these waves are same. The only difference is due to the reflection from the earth surface or due to the path difference, there is a phase difference. So we consider this ED and ER is equal to ES. Take this thing ES common, then we have 1 plus e to the power j alpha plus j beta. We expand this exponential in the term of cos and sine. 1 plus cos alpha plus 180 degree minus j sine alpha plus 180 degree. Okay, and this cos alpha plus 180 degree is equal to minus cos alpha, sine alpha plus 180 degree is equal to minus sine alpha, which make this minus sine became plus. Now, we can write this formula in this form as well, like this is x plus jy, and we can also write the magnitude of x plus jy is equal to under root of x square plus y square into ES. Now again, if we expand this term 1 minus cos alpha, this is 1 plus cos square alpha minus 2 cos alpha plus sine square alpha. Sine square alpha plus cos square alpha is again equals to 1. Then 1 plus 1 minus 2 cos alpha, that is 2 minus 2 cos alpha, and it became ES is equal to 2 1 minus cos alpha. Again, if we expand this thing in the half angle formula, we can write this 1 minus cos alpha is equal to sine square alpha by 2. Now this term became sine square alpha by 2, or we can write ES is equal to under root of 4 sine square alpha by 2. If D is the distance and E naught is the electric field radiated by the transmitting antenna, so the ES, the value of ES that is reached from the receiving antenna is equal to, is nothing but it is field transmitting from the transmitting antenna divided by distance D, and this term is introduced due to the path difference between these two waves. So the total electric field received is equal to this, or we can write it as this value is like as sine of this, and this is nothing but this is your alpha value, which is we calculate over here 4 pi ht hr by lambda d. So now the total field received is equal to 2 E naught by d sine 2 pi ht hr by lambda d, or we can write it as in this formula, in this way. So this is the field received at the distance d from the transmitting antenna. Now again, if we see this term, this multiplication of ht/hr in meter is very small in compared to distance d, which is the distance from the transmitting to the receiving antenna, which is in kilometer. So this small thing is divided by very big thing, then this complete thing became very small, then sine of theta is now equivalent to theta only. So we can remove the sine as well, and we can write this thing as this, or the total field received is equal to 4 pi ht/hr by lambda d square times of field transmitting from the transmitting antenna. So this is the derivation that the what is the amount of field that is received. If we take this thing in power, we can easily convert electric field into the power by this formula. Put these values and we find the electric field in terms of power transmitting from the receiving antenna, that is equal to P. From the transmitting antenna is equal to P. We can find the field in terms of power over here. Thank you for this lecture. In this lecture, we will study about the space wave propagation.